last time I introduced sensory receptors. I told you that sensory receptors are specialized cells or nerve endings in the body. Is stimuli. Receptors generate impulses which provide information to the central nervous system about changes in the internal and external environment. These are actually transducers which convert various forms of energy into the electrical energy, that is action potential or nerve impulse. Stimuli may be electrical, mechanical, chemical, thermal, osmotic. So there are different types of stimuli. When these are applied to the receptors convert these into the nerve impulse or action potential. Sensation is becoming aware of a specific stimulus, say pain sensation, visual sensation, touch sensation. Receptors may be non-encapsulated, without capsule, or encapsulated, having a capsule. We can classify sensory receptors in different ways. The first type of classification is that we divide receptors into 4 types: exteroceptors, interoceptors, proprioceptors, and telo, T-E-L-O, teloceptors. So exteroceptors, interoceptors, proprioceptors, and teloreceptors. Exteroceptors, which respond to stimuli at the surface of the body, which respond to stimuli at the surface of the body, exteroceptors. Interoceptors, which respond to stimuli in the body, say pain receptors, taste receptors, baroreceptors, which respond to blood pressure changes. So these are the interoceptors. Other type is proprioceptors. Proprioceptors, which respond to position and movement. Say I am standing. Receptors are present around the tissue, around the joint. Receptors are present in the tissue around the joints, which inform the nervous system about the position and movement. I am standing or I am moving my arm. So this position and movement impulses are generated by the proprioceptors, which are present in the tissue around the joints. Teloceptors, 4 type, teloceptors, which respond to stimuli at a distance. Say photoreceptors in the retina. Respond to light rays. Receptors in the cochlea respond to the sound waves. Right? So receptors in the cochlea, they respond to sound waves. So this is the first classification. And the second one is the functional classification of sensory receptors. Functional classification of sensory receptors. We divide sensory receptors into 5 types. 5 types of sensory receptors. The first one is mechanoreceptors. Mechanoreceptors. Mechanoreceptors respond to mechanical deformation of the receptor membrane or of the cells adjacent to receptors. So which respond to mechanical deformation of the receptor membrane or of the cells adjacent to the receptors. A number of receptors are included in the mechanoreceptors. Free nerve endings, Merkel discs, hair follicle receptors, Meissner's corpuscles, Pacinian corpuscles, Ruffini's end organs, muscle spindles, Golgi tendon organs, baroreceptors in the carotid, sinus and arch of the aorta, there are baroreceptors. Receptors in the vestibular apparatus, right? So all are the mechanoreceptors which respond to mechanical deformation. The second type of receptors in the functional classification is chemoreceptors, which respond to chemical stimuli, chemical changes, or chemical changes, and these include peripheral and central chemoreceptors. We know peripheral chemoreceptors in the carotid and aortic bodies. Central chemoreceptors in the central chemosensitive area in the medulla oblongata. So central chemoreceptors in the chemosensitive area in the medulla oblongata. Olfactory receptors in the olfactory membrane. Taste receptors in the taste buds. Taste receptors. Osmotic receptors. Osmoreceptors in the anterior hypothalamus. So osmoreceptors in the anterior hypothalamus. Glucostate cells in the satiety center in the hypothalamus. So glucostate cells in the satiety center in the hypothalamus. So these all are the chemoreceptors. Then the third type is thermoreceptors, which respond to temperature changes, So there are 2 types of thermoreceptors: warmth receptors and cold receptors. So warmth receptors and cold receptors. The 4th type of receptors is nociceptors. NOCI, nociceptors, which respond to tissue damage, or which detect tissue damage. So these are the nociceptors which respond to damaging stimuli, painful stimuli, noxious stimuli. So these are the nociceptors. And the 5th type is receptors is electromagnetic receptors. Electromagnetic receptors. So these are the photoreceptors in the retina. So these include the photoreceptors in the retina. So these are the functional types of sensory receptors: mechanoreceptors, chemoreceptors, thermoreceptors, nociceptors, and electromagnetic receptors. So this was about the functional classification of the sensory receptors, or functional types of the sensory receptors. Now discuss about some important receptors, their location, and their function. Now first about the non-encapsulated receptors. Non-encapsulated receptors, receptors without capsule. And these, the first one is free nerve endings. Free nerve endings. Free nerve endings are present in the epidermis of skin, in the GIT mucosa, mucosa of the airways, meninges, periosteum, perichondrium, peritoneum, tympanic membrane, joint capsule, ligaments, muscles, tendons, tympanic membrane, dental pulp. So you have seen wide distribution of the free nerve endings in the body. Right? Now, free nerve endings, which are widely distributed. From free nerve endings, two types of nerve fibers carry impulses. So two types of nerve fibers carry impulses from the free nerve endings. Small nerve fibers which are myelinated, so small nerve fibers which are myelinated, and then fibers which are unmyelinated. These include A delta nerve fibers and C type of nerve fibers. So from free nerve endings, impulses may be carried by A delta nerve fibers and then C nerve fibers. Free nerve endings are involved in the sensation of crude touch, pressure, tickle and itch, pain and temperature. So these are involved in the crude touch, tickle and itch, pressure, pain and temperature. Free nerve endings undergo slow adaptation. So these undergo slow adaptation. We will discuss this later about the adaptation. So these undergo slow adaptation. The next receptors which are encapsulated, which are non-encapsulated, without capsule, these are the Merkel discs. Merkel discs are present in groups, clusters. In the epidermis of skin. So present in groups or clusters in the epidermis of the skin. So these are called tactile dome, D-O-M-E. So tactile domes include the clusters or groups of the Merkel discs. Merkel discs are involved in response to continuous pressure or touch. Say, I'm holding this pen and writing between the tips of fingers. I can feel the pen or pencil with fingertips because of the Merkel disc. So these respond to continuous pressure or touch. These also undergo slow adaptation. So these undergo slow adaptation. Next receptors which are non-encapsulated. Non-encapsulated are hair follicle receptors. These are the hair follicle receptors. These are present around the hair follicles. So these receptors along the nerve fibers are wrapped around the hair follicles. These are stimulated when there is bending of hair. When there is bending of hair. So anything comes in contact with the skin, bending of hair, anybody moving on the skin, bending of hair. So bending of hair stimulate the hair follicle receptors. So anything comes in contact with the skin will cause bending of the hair. Anything moving on the skin will cause bending of the hair. Say any insect which is moving on the skin will cause bending of the hair. So these are very important touch receptors or tactile receptors. So these receptors are very important touch or tactile receptors. These undergo rapid adaptation. So these are the receptors which are non-encapsulated. I told you about the free nerve endings, Merkel discs, and then hair follicle receptors. Now I discuss some receptors which are encapsulated with capsule. And first of these is Meissner's corpuscles. Meissner's corpuscles are present in the dermal papillae. You see, in the dermal papillae, this is the dermal papilla. So these are present in the dermal papillae of the skin of the palm of the hand, sole of the foot, nipples, and external genitalia. Nipples and external genitalia. So these are present in the dermal papillae in the skin of the palm of the hand, sole of the foot, nipples, and external genitalia. Endoneurium of the nerve fiber. Entering this receptor, it becomes continuous with the capsule of the receptor. So endoneurium becomes continuous with the capsule of this receptor. Number of Meissner's corpuscles decreases with age. So their number decreases with age. Meissner's corpuscles respond to fine touch, 2-point tactile discrimination, 2-point tactile discrimination, and vibration. That is low frequency vibration. So these respond to fine touch, 2-point tactile discrimination, and vibration of low frequency, say frequency of 100 Hertz, 80 Hertz. So these receptors respond to low frequency vibration. And then mention about involved in the 2-point tactile discrimination. 2-point tactile discrimination is ability to discriminate two near pointed objects as separate. Ability to discriminate two near pointed objects as separate is the 2-point tactile discrimination. Right? So Meissner's corpuscles involved in fine touch, 2-point tactile discrimination, and vibration of low frequency. These undergo a rapid adaptation. These undergo a rapid adaptation. Next receptors which are encapsulated are the Pacinian corpuscles. Pacinian corpuscles. These are located in the dermis of skin, joint capsule, ligaments, periosteum, perichondrium, fascia. Right? So in the dermis of skin, joint capsule, ligaments, periosteum, perichondrium, fascia. These have thick capsule. So in the Pacinian corpuscle there is thick capsule. Thick capsule. On cut section, the capsule gives appearance of onion, cut onion, pyaz. So on cut section, the thick capsule of Pacinian corpuscle gives appearance of a cut onion. You see, just like a cut onion, on cut section its capsule gives appearance of the cut onion. Pacinian corpuscles respond to movements and high frequency vibration. Movements and high frequency vibration. High frequency vibration. Say vibration of 300 hertz and more than that. Right? So these respond to high frequency vibration and also movement. These also undergo rapid adaptation. So these undergo rapid adaptation. The next receptor which is encapsulated is Ruffini's end organ. Ruffini's end organ. Ruffini's end organs are present in the dermis of skin, you see. So these are in the dermis of the skin. So these are stimulated when skin is stretched or heavy pressure is applied on the skin. So stretching of the skin and heavy pressure on the skin stimulates the Ruffini's end organs. Keep in mind that Pacinian corpuscles and Ruffini's end organs are also proprioceptors. These also act as proprioceptors. I mean the Pacinian corpuscles and Ruffini's end organs, these act as proprioceptors. Ruffini's end organs undergo slow adaptation. So Ruffini's end organs, these undergo slow adaptation. So this was about the important receptors, their location, and then their function. Next we will start discussion on the properties of sensory receptors. Properties of sensory receptors. First very important property of sensory receptors is specificity. Specificity. For a type of receptor, there is a specific stimulus. For a type of receptor, there is a specific stimulus. Or you say, a type of receptor, a particular type of receptor responds to a specific stimulus. Or you say, particular type of receptor is highly sensitive to a specific energy. Right? So a type of stimulus, a type of receptor is highly sensitive to a specific type of energy. So a type of receptor is highly sensitive to a type of energy. Or you say, for receptor type, there is a specific stimulus. So this specific stimulus to which receptor can respond is called adequate stimulus. So specific stimulus to which receptor responds is called adequate stimulus. Receptors can respond to stimuli other than the adequate. Of course, normally receptors respond to adequate stimuli, but these can respond to stimuli other than the adequate. For example, for photoreceptors, what is stimulus? Light. So light rays are the stimulus for the photoreceptors in the retina. But if you exert firm pressure over the eyeball, light halos are seen. So you close your eyes and exert firm pressure over the eyeball, light halos are seen. So the photoreceptors responded to the heavy pressure exerted on the eyeball. Keep in mind that each principal type of sensation is a modality of sensation. So each principal type of sensation is the modality of sensation. Say pain is modality of sensation. Vision is modality of sensation. Touch is modality of sensation. Now for a specific sensation, there are special nerve pathways. There are specific nerve pathways. And these nerve pathways terminate on a specific part of the brain. So for a specific sensation, a specific pathway, specific sensory pathway, and this terminates to a specific part of the brain. Say, for vision, there is visual pathway. And where does the visual pathway terminate? Into the visual cortex. It terminates into the visual cortex. Specificity of the nerve pathway to transmit one modality of sensation is called labeled line principle. So specificity of the nerve pathway to transmit only one modality of sensation is called labeled line. Labeled line principle. So specificity of the nerve pathway to transmit impulses of only one modality of sensation is called labeled line pathway. In addition, it is also called Muller's law of specific nerve energy. Muller's law of specific nerve energy. Muller's law of specific nerve energy. Right? So, for specific sensation, specific nerve pathway carry impulses to a specific part of the brain. And this specificity of the nerve fiber to transmit impulses of one modality of sensation is called labeled line principle. And it's also called Muller's law of specific nerve energy, that for specific sensation, specific pathway carry impulses to a specific part of the brain. We're discussing about the labeled line principle or the Muller's law of specific nerve energy, and that is for specific sensation, specific nerve pathway carry impulses to a specific part of the brain. So when this nerve pathway or these nerve fibers are stimulated, and these nerve fibers are stimulated by any method, and any point in the pathway, the sensation perceived will be that for this pathway specific. Right? So you stimulate this pathway by any method, at any point in the pathway, the sensation perceived will be that for which the pathway is specific. So the person perceives the sensation for which this pathway is specific. Right? So I told you that you stimulate the specific pathway for a specific sensation by any method, at any point in the pathway. The subject perceives the sensation for which this pathway is specific. Moreover, there is also law of projection. There is also law of projection. That is, when you apply a stimulus, the stimulus is perceived, localized, and projected to a part of the body. You apply stimulus on a part of the body. The stimulus is localized and projected to a part of the body. Say, my right hand is touched by the marker. So touching of the marker is perceived. And where is it localized? Projected to the right hand. To the right hand, not left hand. Right? So I touches this marker to my right hand. This touching of the right hand is, of course, localized, projected to the right hand, not to the left hand. Right? This is the law of projection and localization. Actually, from the receptors of a particular part of the body, from the receptors of a particular part of the body, specific nerve fibers carry impulses. Specific nerve fibers carry impulses. So when these nerve fibers carrying impulses from receptors of a specific part of the body, these are stimulated. The stimulus will be localized, projected to that particular part. I told you, from receptor of a particular part of the body, specific nerve fibers carry impulse. And when these nerve fibers are stimulated, the stimulus is localized and projected to that specific part, say the right hand. Right? So this is the basis of a phenomenon seen, which is called phantom limb. Phantom limb. Phantom limb. Phantom limb. person during road accident got severe injury to the right leg. Right? A patient, a subject, a man, got severe injury in road accident, and his right leg was amputated at knee. His right leg was amputated at the knee. At the knee. Now, sometimes he complains of proprioception and pain in the right lower leg, which is not there, which was amputated. Right? So patient is having amputated lower leg at knee level, and sometimes the patient complains of proprioception, proprioceptive impulses, and pain in the lower right leg, which is not there, it is missing. This is called phantom limb. Phantom limb. So patient complains of severe proprioceptive impulses and pain in the right lower leg, which is missing, which was amputated. Reason is that in the end, that is the amputated stump, the leg was amputated, right? So in the stump, cut nerve endings of the nerve fibers, which were carrying impulses of the lower leg are present. And pressure or any irritation of the cut ends of these nerve fibers results into stimulation of these nerve fibers. And these nerve fibers were carrying impulses from right lower leg before the amputation. So the cut ends of nerve fibers which were carrying impulses from the right lower leg, these cut nerve endings are stimulated, irritated in the stump, and this results into the feeling of pain and proprioception in the right lower leg, which was not there, which has been amputated. This is called phantom limb. Phantom limb. Now I have discussed the property of specificity, right? Weber-like principle, Muller's law of specific nerve energy, and then about the phantom limb, which is because of the law of projection, right, and localization.